Exomars is a multi-part Europeanled program to explore Mars, both on the surface and from above. The program has two phases in the works. The components of the first phase, the Trace Gas Orbiter TGO and Schiaparelli, a landing demonstrator, both arrived at Mars in October 2016. Schiaparelli failed during landing, but TGO remains in excellent health and is preparing for its science mission. The main science mission is expected to begin in 2018, when TGO reaches its nominal orbit. The orbiter will be in place to provide communications for the second phase, the Exomars rover and landing surface platform, which are expected to launch in 2020. The program has changed several times during the past 2 decades, starting with sole European involvement, then including NASA, then including Roscosmos, the Russian space agency. Instead, in 2001, ESA started Exomars as part of the larger Aurora program, which was to have taken humans to Mars. Aurora was supposed to include a rover in orbiter that would have launched in 2009, and a Mars sample return mission that would have launched sometime afterward. Development delays, which are common on space missions, pushed the first phase of Exomars beyond that date. However, Exomars was formally approved by the ESA member states in 2005. In 2008, ESA's Ministerial Council recommended that the Europeans look for international partners to participate in Exomars. At the time, NASA was re-evaluating its own Mars missions after the Curiosity rover was delayed from a planned 2009 launch to 2011. In 2009, NASA and ESA signed a Mars Exploration Joint Initiative that was supposed to meet the goals of both Exomars and the planned NASA Mars Science Orbiter. The missions were restructured into 2 phases. The first phase, which would launch in 2016, was supposed to include a European orbiter and landing demonstrator module, which later became the Trace Gas Orbiter TGO and Schiaparelli. The second phase initially was planned to include 2 rovers, but was deemed too complex and scaled back to 1 European rover with U.S. instruments. In 2012, however, NASA pulled out of Exomars. NASA's James Webb Space Telescope, now expected to launch in 2018, exceeded its budget, and the agency restructured several other missions to address the shortfall. ESA then made an agreement with Roscosmos to replace the launch vehicles and parts of the payloads that NASA was supposed to provide. With the agreement in place, TGO and Schiaparelli launched in 2016 as planned. The European rover and a Russian landing platform were expected to launch in 2018, but delays with industrial activities and the payloads pushed that back 2 years to 2020. Mars launch opportunities from Earth only take place roughly every 2 years, when the planets are relatively close to each other and a spacecraft can use a minimum of fuel to get there. The goal of the Trace Gas Orbiter TGO is to search for less abundant components of the Martian atmosphere. The Martian atmosphere is mostly made up of carbon dioxide, but concentrations of other molecules are poorly understood. For example, methane, a sign of either biological and geological activity, has been measured in different concentrations by different ground-based telescopes. The Curiosity rover found a spike in methane during one season on Mars that was not repeated the next year. So, these measured variations in methane could be due to true variations on the surface, although more information is needed to be sure. Since methane is short-lived on geological time scales, its presence implies the existence of an active, current source of methane. It is not clear, yet, whether the nature of that source is biological or chemical, ESA stated. Organisms on Earth release methane as they digest nutrients. However, other purely geological processes, such as the oxidation of certain minerals, also release methane. TGO and the landing demonstrator Schiaparelli were launched together on March 14, 2016, from a Proton rocket from Baikonur, Kazakhstan. TGO successfully entered orbit at Mars on October 19, 2016, the same day of Schiaparelli's landing attempt, which failed. The spacecraft was inserted into a highly elliptical orbit at Mars that takes 4 Earth days to complete. To perform its main science mission, it must be lowered into a near-circular altitude of about 400 kilometers (250 miles) and have a 2-hour orbit. Starting in 2017, mission controllers will make a series of controlled skims through the edge of the Martian atmosphere. This technique is called aerobraking and has been performed by several other Mars missions, as well as the European Venus Express mission. Aerobraking will continue until early 2018. The orbiter is still being tested ahead of its main science mission. In late November 2016, it performed calibrations of its instruments and took some test images of the surface. The camera also imaged the moon Phobos on November 26. TGO has 4 principal instruments: Nomad, Nadir and Occultation for Mars discovery, a package of 3 spectrometers, 2 infrared, 1 ultraviolet to identify methane and other parts of the atmosphere. Some elements will be found by looking at the atmosphere with the sun behind it, while others will be examined by direct reflected light observations. Atmospheric chemistry. 3 infrared instruments will provide information on the Martian atmosphere's chemistry and structure. CAS's color and stereo surface imaging system provides high-resolution images of the surface that will give geological context and the possible sources or sinks for trace gases found by Nomad and AX. Fine-resolution epithermal neutron detector maps potential deposits of water ice by looking for hydrogen on the surface to depths of up to 1 meter 3 feet. Besides its science mission, TGO is expected to serve as a communications relay for the Exomars 2020 rover when it reaches the Martian surface. TGO was supposed to send communications from the failed Schiaparelli lander to Earth, but that part of the mission was never realized. Schiaparelli was supposed to demonstrate ESA's capability to perform a controlled landing on the surface of Mars. The module rode to Mars with TGO, but it failed during landing. It separated from TGO as planned on October 14, 2016, and was activated shortly before entering the Martian atmosphere 3 days later. Its parachute was supposed to be deployed about 11 kilometers 7 miles above the surface. At that point, Schiaparelli was supposed to jettison its front and rear heat shields, turn on instruments to find its landing point in Meridiani Planum, then turn on its engines to reduce its velocity. The landing shock was intended to be lessened using a crushable structure. Schiaparelli was supposed to last 2 to 4 days on the surface. Schiaparelli lost communication with TGO and by extension, with Earth during descent. The entire landing sequence was performed automatically due to the time delay between Earth and Mars, so there was nothing controllers could do but monitor the situation and assess the aftermath. Evidence of its crash site was photographed by NASA's Mars Reconnaissance Orbiter 2 days after the malfunction, and further pictures were sent in over several weeks. In November 2016, ESA said Schiaparelli's parachute and Doppler altimeter worked correctly, but there was a problem concerning the inertial measurement unit, which measures rotation rates. ESA said the IMU exceeded its maximum measurement rates for 1 second, or longer than what was expected. When merged into the navigation system, the erroneous information generated an estimated altitude that was negative, that is, below ground level, ESA said. This in turn successively triggered a premature release of the parachute and the back shell, a brief firing of the braking thrusters, and finally activation of the on-ground systems as if Schiaparelli had already landed. In reality, the vehicle was still at an altitude of around 3.7 kilometers (2.3 miles). More information is expected in 2017 from an independent inquiry board. Science instruments on the lander included DREAMS dust characterization, risk assessment, and environment analyzer on the Martian surface. The package included METWIND to measure wind speed and direction, DREAMSH humidity, DREAMSP pressure, MARSTM atmospheric temperature close to the surface, solar irradiance sensor transparency of the atmosphere, and microarrays atmospheric radiation and electricity sensor. Amelia atmospheric Mars Angrian landing investigation and analysis. This was to look at Schiaparelli's engineering data to learn its trajectory to the surface, and to look at the Martian atmosphere's density and wind during the descent. The information was intended to make better models of the Martian atmosphere. COMARS combined aerothermal and radiometer sensors, which was attached to the back cover of Schiaparelli. It was supposed to measure parameters such as Schiaparelli's surface temperature, the rate at which heat energy was transferred to the surface, and the amount of radiated heat from the hot gas to the back cover. The goal was to better understand how to build spacecraft to withstand entry, descent and landing on Mars. DECA, a descent camera, to take images during the descent. INRRI instrument for land grooving laser retroreflector investigations, which was essentially an instrument that allowed Martian rovers to find Schiaparelli on the surface through retroreflection, a technique that was also used for instruments on the Apollo missions to the Moon in the 1960s and 1970s. The instrument was also expected to help test laser communications between the surface and orbit, to find trace elements in the atmosphere, and to see how much dust buildup occurred on Schiaparelli. The Exomars 2020 mission will include a European rover and a Russian surface platform. The rover will provide information about potential signatures of life on Mars, specifically by looking at environments where water could have flowed. It also will carry a drill that can penetrate up to 2 meters 6 feet below the surface. The rover and surface platform will travel together to Mars inside a European carrier module. Shortly before descent, a Russian-led descent module will separate from the carrier and bring the rover and surface platform to the surface, using elements such as parachutes and thrusters to reduce the speed of landing. After landing, the rover will leave the landing platform behind to move around Mars and look for organic material from the planet's past. Meanwhile, the surface platform, which is stationary, is expected to operate for about 1 year. The platform will take pictures of the landing site, watch the local weather, probe the internal structure of Mars, and do investigations of the atmosphere. It also will look at subsurface water distribution and radiation around the landing site, in comparison with measurements from TGO. The primary objective is to land the rover at a site with high potential for finding well-preserved organic material, particularly from the very early history of the planet. ESA said the rover will establish the physical and chemical properties of Martian samples, mainly from the subsurface. Underground samples are more likely to include biomarkers, since the tenuous Martian atmosphere offers little protection from radiation and photochemistry at the surface. The drill is designed to extract samples from various depths, down to a maximum of 2 meters. Instruments on the rover include PanCam panoramic camera, ISEM infrared spectrometer for Exomars, CLUPI close-up imager, wisdom water ice and subsurface deposit observation on Mars, EDRIN, which will look for subsurface water and hydrated minerals, in combination with wisdom MA_Miss Mars multispectral imager for subsurface studies, micromega visible and infrared imaging spectrometer, RLS Raman spectrometer, MOMA Mars organic molecule analyzer. Instruments on the surface platform include LARA lander radio science experiment, habitability, brine, irradiation and temperature package, METEOM a meteorological package. This includes sensors to measure pressure, METEOP, humidity, METEOH, radiation and dust, RDM, and magnetic field, SOMR. MAGRAY a magnetometer, including a wave analyzer module, AMTSPP, cameras, BIP instrument interface and memory unit, fast IR Fourier spectrometer to study the atmosphere, ADRONEM active neutron spectrometer and dosimeter, MDLS multi-channel diode laser spectrometer for atmospheric investigations, PATM radiothermometer for soil temperatures, including below the surface, a dust sweep to look at dust particle size, impact and atmospheric charging, SEM a seismometer, MGAP gas chromatography, mass spectrometry for atmospheric analysis. A landing site will be selected about 6 months before the mission launches in 2020. When the rover was originally expected to launch in 2018, ESA's landing site selection working group recommended landing in Oxia Planum. However, another site may be selected due to the 2-year mission delay. The region has very old rocks, 3.9 billion years old, that have a lot of clay, which means that water flowed there in the past. Further, biosignatures may have been preserved thanks to volcanic activity that covered over the clay. Additional resource.